Hello AP Statistics students. In this video, we're going to take a closer look at the one sample t-test for a population mean. So we did this in class already, right? But we just let the calculator do all the heavy lifting. Now it's time to actually delve into what a one sample t-test is. All right, what's the math that's working on in the background? It's important that we understand this. Even though most of the time the calculator is going to do most of the work for us. So mostly we need to be able to understand the math so that we can use a standardized test statistic to find a p-value. Because sometimes you'll only get the standardized test statistic. You won't get the actual data or all the other things you need to plug into the calculator. So let's do this. Let's just going to do the same scenario we had from class. We've got some Amazon batteries and we want to test whether or not they are better than Duracell batteries. And the Duracell batteries last 30 hours. So we want to know, is there convincing evidence at the alpha 0.05 level that Amazon basic batteries last longer than 30 hours? So we have our null and alternative hypotheses over here. So the null is that they're the same, all right, no difference, they equal 30, and our alternative is that they are greater than 30 hours. So I don't have it here, but we took a sample, right? I had the sample data before where the mean is 33.93 and the standard deviation of the sample is 9.82, and we had a sample size of 15. So what actually happens? What math is the calculator doing? Well, after our assumptions are all, or our conditions are all met, right? The conditions for inference, we build our sampling distribution. Now, in this case, interesting, for means, this sampling distribution follows a t-distribution. Not quite normal. Well, it would be normal if we knew the population standard deviation, right? If we knew the actual population standard deviation, then we could use a normal model. But sadly, we don't. All right? We only can use the sample's standard deviation as an approximation. And when that's the case, we have to use the t-distribution. Now, of course, when I draw this, it's still going to look normal because you can't really tell the difference between the two when you're just drawing it by hand. But there's my t-distribution. The center here would be the null. Remember, we assume the null is true. So the center would be 30. The standard deviation here, which we estimate with the standard error, is our standard deviation, 9.82, divided by the square root of the sample size, which was 15. So in this case, 9.82 divided by the square root of 15. Again, this formula is on the formula sheet, right? It's just the formula for the standard error of a sampling distribution. 2.54, let's go 2.54. Probably enough decimals. And so that is our standard deviation that we would add and subtract here, right? Now, our sample that we got was 33.93. So what's the probability of getting a sample like that? Well, 33.93 is right here-ish somewhere maybe. And so we would want this area. Normal CDF vibes, right? Well, actually, not normal CDF vibes, because we don't have a normal curve. We have a t-distribution. So yes, we essentially want a t TCDF. Not a normal CDF, a TCDF, to find that area. So with this though, when we type this into the calculator, let me put my boundary. My boundary here is 33.93, right? When we type this into the calculator, we can't type it in that way. All right, we can't use the context. We can't use the context of 30 and 33.93. Those are all about batteries. What we have to do is standardize those numbers. We're essentially going to turn them into z-scores. Okay, just make it, we're going to standardize the number line. So the middle will be 0. And the boundary here, let me use green again. The boundary is going to be how many standard errors away. It's basically a z-score. And we call that the standardized test statistic. So the standardized test statistic. So to find that, it is basically a z-score. So in this case, because it's a t value, we use t is equal to our statistic, 33.93, minus the middle, 30, divided by the standard error, which is 2.54. Hopefully you can see that that is essentially a z-score, right? It is our average from the sample minus what our assumed population mean is. All right, we're assuming the null is true, divided by the standard deviation, or in this case, we're estimating that with the standard error. How many standard errors away is it? So just throw that into the calculator, figure that out. So 33.93 minus 30 divided by 2.54 gives us a t statistic here of 1.5. Let's round it up, 5. So our t statistic is 1.55. It's 1.55 standard errors away from the middle. And that's the number we're going to type into our calculator right now. Because we can't do it with context, with the 30 and the 33, we have to use the standardized numbers. And so we're going to find the area above 1.55. So when I go to my calculator here, so I go second distribution. There we've got the normal CDF that we know and love, the inverse norm, the inverse T, and then down to number 6, the TCDF. All right, it's the cumulative density function for a T distribution. So we have the lower, the upper, and the degrees of freedom. So you see it does not let us type in our own mean of 30. It doesn't let us change what the t distribution is like we can for a normal. All right, the default is just always going to be 0. All right, so what's our boundary here? Our lower boundary is 1.55. Our upper, well, it goes up forever, so just put a really, really, really big number in there. And the degrees of freedom. If our sample size was 15, that is 14 then, right? So here we are finding that area, 0.0717. That number should sound a little familiar, right? So again, the two things we just found, the standardized test statistic gives us a p-value of 0.0717, which we can then find or make our conclusion off of, right? In this case, I think we failed to reject because our alpha was 0.05. But again, it's just how we can use a cumulative density function, not a normal CDF, but a TCDF, to find the probability of getting a sample like ours. And just to show you one more time, that's exactly what the calculator does for you when you let it do the whole thing. So if I go stat tests and I run a t-test off of these numbers, where are they? Right there. So, not data, I want stats. Our null was 30. Our sample average was 33.93. Our standard deviation of the sample, 9.82. And our sample size was 15. We want to know if it's bigger than the null. So I'm going to draw this. And as you can see, we have the exact same picture that we have drawn. Our t-value is 1.55, so this is 1.55 standard errors away, and the area, the p-value, is 0.0717. Exactly, here we go, exactly what we have here. So that's what's happening in the background, okay? Do you need to do this? Oftentimes, no. Oftentimes, no, because you're just going to let the calculator do it for you. But it is important to know some of the math that's happening in the background, especially if you see some things about the standardized test statistic, so you know where that comes from. Sometimes you might even see it all plugged in as one big formula. T is equal to x bar minus the null divided by the standard error. Well, what's the standard error? It is the standard deviation of the sample divided by the square root of the sample size, right? We did that up here as a separate step, but sometimes you'll see it all as one big formula plugged in also. We do need to be familiar with that. Now, another reason why we need to be familiar with it is sometimes you'll get an obnoxious question like this that just doesn't give you all the information. So Daisy was testing a null hypothesis that the mean was equal to 33 versus the alternative hypothesis that it's greater than 33 with a sample of 11. Her test statistic was t equals 1.368. Assume that the conditions for inference were met. What is the approximate p-value for her test? Well, that's obnoxious because we don't have the sample statistics. So we can't plug this into our test on the calculator. We are forced to do the TCDF. All right, we have ourselves a t distribution for our sampling distribution. 0 is in the middle. And the test statistic, the boundary over here, is 1.368. Our null is that it was greater than 33. So we want, again, a TCDF greater than 1.368. We don't know what the context is, but we do know what the test statistic is, so we can simply go from there. So let's see. So let's go second quit here. We're going to go second distribution, TCDF, because I want the area of that curve above 1.368. So 1.368. Upper bound is still a big number. My degrees of freedom this time, however, they said they had 11 observations, so that means I have 10 degrees of freedom. So our p-value is 10%, 0.10. So sometimes we can force you to use the t-statistic, the standardized test statistic, by not telling you much about the sample. Otherwise, you're just doing everything on the calculator. All right, I hope that makes some sense about the math that's happening behind the scenes of that calculator command. It is important to sort of understand all of that background.